From the dawn of human existence, one profound and haunting question has followed us across ages, whispered in myths, investigated in laboratories, and contemplated in quiet moments beneath the stars: how did life begin on Earth? This question is more than just scientific, it is existential. It is the foundation of all inquiries into who we are and where we belong in the vast cosmos. Whether in ancient fireside stories or in modern observatories, humanity has always been drawn to the mystery of origins. To ask where life came from is to connect ourselves with something infinitely greater than our individual span of years, to see our fragile lives as part of an unbroken chain extending back billions of years, to an unfathomable beginning. It is a question humbling in scope, one that has inspired poets to imagine gods molding life from clay and scientists to trace molecules assembling in primordial seas. Yet, despite centuries of effort, no single, final answer has ever been agreed upon. This uncertainty is not a failure. In fact, it is part of the wonder. To live with the mystery is to stand like a traveler at the shore of a vast ocean, gazing out into waters that shimmer endlessly into the horizon. We are explorers of time, and the map of life's beginning remains beautifully incomplete. What we do have, however, are clues, scientific models, experiments, geological evidence that guide our imagination and provide glimpses into how it all might have unfolded. The deeper one looks, the more astonishing the possible pathways become. So let us step onto this journey together, not merely to seek facts, but to embrace the awe they stir within us. Close your eyes, if you wish, as though preparing to rest. Allow the present moment to loosen its grip. Hear the quiet in your surroundings, feel your breath settle, and imagine the curtain of time beginning to draw back. The cities, the forests, the continents shaped by millions of years of history, all fade away. One by one, the familiar shapes of today's Earth vanish, until you find yourself drifting backward into an age so distant that human memory cannot reach it, an age when the Earth itself had barely begun its story. 4.5 billion years ago, Earth was no serene blue planet filled with forests, oceans, and life. Instead, it was wild and alien, a place still molten from its birth. The young Earth had gathered from clouds of cosmic dust left after the Sun's formation, its surface heaving with volcanic seas of liquid rock. The air above was heavy with thick gases: methane, ammonia, carbon dioxide, and water vapor rolling through an atmosphere unlike anything we know. Towering plumes of fire rose from endless fissures, while colossal asteroids and comets bombarded the surface, each impact releasing unimaginable energy. Lightning split the darkened skies in constant flashes, illuminating oceans of lava. Nothing gentle existed here. To exist on Earth then was to exist amid fire and thunder, silence and chaos. Yet within this violent crucible, possibility hid. The same destructive forces that tore the young planet apart were also stirring its greatest potential. The volcanic eruptions threw minerals into the air and sea. Thunderstorms delivered sparks of raw energy into chemical soups. The oceans and the atmosphere mixed and collided, creating an endless cycle of reactions. It was as though the planet was a vast experiment, every moment producing new combinations of atoms, new chances for creation. To look upon that world now even only through imagination is to recognize not only a scene of destruction, but a prelude. For though no life walked the steaming ground, everything necessary for life's emergence had already been scattered across land, sea, and air. And so the question sharpens: how could lifeless matter transform itself into something that breathes, grows, reproduces, evolves, and, one day, contemplates its own origins. At its heart, this puzzle brings us to the edge of an almost magical moment, the crossing of the line from chemistry into biology. Imagine countless atoms drifting into collisions in warm pools, in stormy seas, or beneath volcanic vents deep in the ocean floor. Alone, they are only particles, nothing more than specks of matter. But given energy and given time, they begin to form ever more sophisticated molecules, chains, spirals, lattices of astonishing resilience. Step by step, they build capacity, not consciously, but inevitably, until eventually a molecule appears that can copy itself, perhaps imperfectly, passing information forward. That subtle leap is the first spark of something that behaves like life. Different cultures, in different times, have explored the mystery of beginnings in their own language. In myth, God sculpted humans from earth or breathed spirit into clay. In modern science, we speak instead of amino acids forming on lightning-scorched plains, or complex organics arriving from comets streaking across the sky. Both images, poetic and scientific, remind us of the same truth that life's origin is a story of transformation. Out of the chaotic elements of a raw planet, something new emerged that had never been before, a system capable of not only existing, but continuing, persisting, and multiplying. Pause for a moment. Let that vision fill your imagination. Picture the vast oceans, constantly swirling. Picture a lightning bolt striking the surface, a brilliant flash in an endless storm. Beneath it, molecules tremble, reconfigure, and some cling together in fragile chains. This is not life yet. Not exactly. And yet, it is a beginning. For in every drop of water, a billion invisible rehearsals are playing out trials, failures, successes, and the faint but persistent drive toward complexity. Today, when you breathe, when your heart beats, when your mind drifts toward sleep, you are continuing this story. It is not something foreign to you. You are not a separate witness observing life's distant birth, you are a descendant of it. In every cell that makes up your body, the record of that ancient transformation is still written. Spiraled within your DNA, shaped over billions of years, lies the whisper of oceans struck by lightning, of volcanic pools giving birth to the first reactions. You are living evidence that what began so long ago has not only endured but has blossomed into unimaginable diversity. And if you let yourself drift further into the thought, you may see that the question "how did life begin?" is not entirely separate from the question "how did I begin?" For your very existence is a chapter nested within that larger story. Without the fragile leaps made by molecules in pools of ancient water, there would be no plants, no animals, no humans, no you. The life within you is a continuation, a song begun billions of years ago, still unfolding in the present moment. As this part of the documentary closes, remember that the search for life's beginnings is not about reaching a cold, clinical solution. It is about wonder. To contemplate the birth of life is to contemplate the poetry of matter itself. The earth was once an unlivable sphere of storms and fire, and yet, from within that apparent chaos, a subtle harmony arose, one that has led across epochs to forests, to stars reflected in oceans, to laughter, love, and consciousness. The eternal question remains. Scientists still investigate, philosophers still imagine, poets still tell stories. Perhaps the complete answer will never be within our grasp. And perhaps that is as it should be. For mystery itself is part of the human experience. Tonight, as you sink toward rest, you too can inhabit that question, not needing to solve it, only to feel its wonder. Let go, surrender to calm breath, and remember that in your existence lies proof of the most extraordinary transformation the planet has ever known. You are the continuation of life's greatest story. When you imagine Earth today, you see the blue planet filled with oceans, continents, swirling clouds, and the green breath of forests covering the land. But if we travel back far enough, billions of years into the past, the image unravels into something almost unrecognizable. Earth was then a very different place, not the gentle cradle of life, but a harsh, violent, and chaotic world still shaping itself from the debris of cosmic birth. To enter that ancient time is to step into a landscape of extremes, where fire and water, light and darkness, birth and destruction collided endlessly, sculpting the foundation of the living world to come. 4.5 billion years ago, the young Earth spun beneath a sun that was itself still young. The skies burned with dust left from the solar system's formation, the last fragments of a collapsing cloud that had given birth to the central star. Planets formed one by one from clumps of rock and ice drawn together by gravity's unseen pull. Earth, one among them, gathered rapidly, its mass swelling with every collision of asteroid and comet. Each impact released waves of unimaginable energy, melting the rock, reshaping the crust, until the entire surface glowed with the heat of creation. For millions of years, this bombardment continued, a rain of fire from the heavens, tearing holes in the planet's shell, then sealing them again with lava, over and over, in a relentless cycle of destruction. Yet even as Earth endured this trial of fire, the seeds of its identity were already being sown. Deep within its molten core, metals began to separate from rock, heavy elements like iron sinking inward, shaping the dense interior, while lighter silicates floated above, forming the foundation of continents yet to appear. From this process came the geomagnetic field, a silent shield that would much later protect the fragile beginnings of life from harmful solar winds. It is strange to think that even in its earliest violence, Earth was quietly preparing for the existence of living beings. Even before oceans formed, even before the air grew breathable, the planet was carving out the conditions that would one day allow cells to flourish. But to stand on Earth then, if it had been possible, would have been to stand inside a nightmare. Volcanoes ruptured the surface in endless fury. Mountains rose and collapsed in rapid succession, for the crust was young, thin, and unstable. Rivers of molten rock threaded across the landscape, glowing beneath skies dark with ash. The air was thick, toxic, heavy with steam. There was no oxygen yet, no clean breath. Instead, the atmosphere swirled with gases exhaled from the depths, carbon dioxide, methane, sulfur compounds, and ammonia. This was not air fit for lungs, nor skies fit for gentle weather. And yet, paradoxically, it was precisely this strange cocktail of gases that would later prove essential for life's beginning. Let us step closer, slow our imagining, and listen. Hear the constant rumble of the young planet, a throbbing like the heartbeat of something alive. The ground shakes with endless quakes. Fire pours upward, painting the horizon in red light. And within the air, thunder cracks repeatedly, lightning forking into the brewing storms. The energy is unrelenting, striking the oceans, vaporizing the surface, and then condensing again into rain that falls ceaselessly, hammering the hot earth in floods as if the skies themselves were trying to cool the restless world. Imagine raining for centuries, for millennia, oceans filling drop by drop, rushing into craters, pooling on the raw crust, creating seas vast enough to encircle the globe. This was the beginning of water's dominion, a dominion that continues today, for 3/4 of Earth remains covered by the descendants of those ancient rains. The oceans, however, were not merely gentle expanses of cooling water. They were experiments in progress. As rain fell through an atmosphere laden with chemicals, it absorbed them. As rivers rolled across volcanic plains, they carried minerals into the seas. Slowly, the oceans became more than water. They became a vast chemical cauldron, a canvas upon which the raw possibilities of life were painted. Every wave stirred molecules together. Every tide mixed elements in new arrangements. And every lightning strike, every ray of sunlight, every plume of volcanic heat was a hand, unseen but ceaseless, scribbling into the chemistry of the deep. But how, one might ask, could a place so violent foster life? How could such extremes, the sulfurous fumes of volcanoes, the crushing bombardments from space, the scalding heat of a surface still cooling, become the setting for something as fragile as living matter? The paradox is profound. Earth's violence was both its danger and its gift. Without the constant impacts from asteroids, Earth would not have received so much of its water, for comets and icy bodies helped deliver oceans to the planet's surface. Without volcanic outgassing, there would have been no air, no carbon dioxide, no nitrogen, no methane to feed the chemical reactions of early biochemistry. Without lightning flashing thousands of times each day, the oceans would have remained inert, mere water rather than the restless mixture needed to stir life's first whispers. Destruction and creation entwined, inseparable. And it is from this inseparability that the real story of life begins. At first glance, this world would appear utterly lifeless, an inferno of stone, smoke, and water. But linger there long enough, let your imagination rest upon that landscape. You might begin to see a kind of hidden purpose coursing through the chaos. Consider the balance, heat and cooling, fire and flood, matter and energy. It was as if Earth were rehearsing the principles of life before life itself emerged, practicing the mixing, the cycles, the flows that living organisms would later embody in their cells and blood. The rains did not stop. For millions upon millions of years, the sky emptied itself upon the earth in torrents so vast that it seemed as if the heavens themselves were dissolving into the seas. Water pooled into ancient basins carved by impacts, filling craters with deep blue shadows. It spread across the scarred crust, connecting, merging, until the first oceans of Earth began to take form. These waters were nothing like the calm oceans you may picture today. They boiled with heat left from the planet's angry core, they frothed with bubbling minerals spewed by endless volcanoes, and they shimmered with particles carried down by storms that never rested. The seas were heavy, thick with dissolved chemicals, and they shimmered under a sun whose light was weaker than the one we know, for the sun too was young, still finding its strength. Yet in those dim, restless waters, the conditions began to assemble almost perfectly for chemistry to take an extraordinary leap. Imagine standing on the shore of that ancient sea, if shore is even the right word, for land then was jagged, steaming, unsteady, broken frequently by eruptions and earthquake cracks. The ocean stretched ahead, its surface restless, battered by rainfall, its depth stirred by currents hotter than any modern rift. The smell of sulfur filled the air, the taste of metal hung in the droplets landing on your tongue. Clouds swirled ceaselessly overhead, as if they too were alive, and through them, lightning burned the sky again and again like the drumbeats of a primeval heart. Each strike of lightning carried energy into the waters. Molecules shivered, snapped, and reformed. Hydrogen met carbon. Nitrogen met oxygen. Simple gases drifted together, and, against probability, began forming longer, more resilient chains. These were not yet alive. They did not breathe or dream or multiply. But they held something new, structure. They contained the building blocks of complexity. In the oceans of the young Earth, the story had only barely opened its first page, but already, the letters of life were being written tiny, almost invisible, strung together by lightning, fire, and time. Below the waves, the ocean floor split with fissures that bled heat and minerals into the water. Hydrothermal vents, perhaps hundreds of thousands of them, released streams of superheated liquid rich with iron, sulfur, and carbon. Out of their mouths poured nutrients and energy, churning the nearby waters into swirling clouds of chemical abundance. These vents acted like natural laboratories, places where the chemistry of life might have been tested again and again. Picture the dark seafloor. There are no fish, no corals, no glowing creatures as you might see today. Only emptiness, blackness, silence except for the smoke-like plumes rising from vents, shimmering in the cold, dense water. Around them, minerals crystallize, forming chimneys that stand like towers in the abyss. Against those chimneys, molecules collide in the heated turbulence. They attach, they split, they reattach, gradually increasing in complexity. Over millions of years, this process repeated endlessly, an orchestra of trial and error. Some scientists believe that here, in these crucibles of fire and water, life may have first emerged. The constant supply of heat kept reactions alive, while mineral surfaces acted like templates, guiding molecules to attach in precise ways. It was as if the Earth itself were experimenting, trying combinations over and over, waiting for one sequence to persist, to stabilize, to begin something fundamentally new, self-replication. But the vents were not the only stage of possibility. Across the surface of continents, shallow pools formed in volcanic craters and depressions left behind by collapsing land. These pools, warmed by the sun, concentrated minerals as water slowly evaporated. Here two molecules gathered, growing closer and closer, merging into membranes, into droplets that resembled primitive cells. Evaporation, rainfall, drying, flooding cycles repeated endlessly, teaching molecules resilience, giving them a rhythm that echoed what metabolism would later become. Life's story, it seems, was not destined for just one location. It rehearsed itself everywhere, in vents, in pools, in crashing seas, even in the very clouds. Everywhere on the young Earth, the conditions of possibility expanded outward, as if the entire planet were conspiring with itself to give rise to a spark it did not yet know how to name. While the oceans brewed their mysteries, the heavens above still raged. The young sun was unpredictable. Its surface erupted with violent radiation, streams of solar particles that spilled across space. Some might think this bombardment would have sterilized the Earth, stripping it of potential. But deep in Earth's belly, the molten core was turning. Iron, heavy and liquid, churned in slow but powerful circles, and in doing so, it gave birth to something invisible yet essential, Earth's magnetic field. This magnetic shield, stretching outward into space, bent the sun's deadly winds away. It created a safe zone around the planet, sheltering its fragile atmosphere from being stripped apart. Without it, Earth's gases would have been lost. Without it, Earth's seas would have boiled away into emptiness. Instead, the shield held firm, and beneath its protection, storms remained Earth's own, and oceans were allowed to grow, deepen, and stabilize. At the same time, enormous impacts continued from space debris, the leftovers of planetary formation. Each collision was catastrophic, releasing energy brighter than 1,000 suns. Some vaporized seas, others melted whole regions of crust. Yet strangely, many of these impacts may have delivered critical chemical gifts. Comets carried water, asteroids carried carbon compounds, frozen ices delivered nitrogen. Each strike, though devastating, also contributed ingredients to the growing recipe of possibility. Thus, in every act of destruction, Earth gathered abundance. The line between chaos and creation blurred entirely. As eons passed, the Earth's face began to stabilize. Volcanoes still erupted, oceans still frothed, lightning still split the air, but already, the planet had transformed from a surface of endless bombardment into one more capable of nurturing what it had quietly been preparing. The crust thickened, continents hinted at their outlines, seas deepened into stability. In this world, silence fell not in sound but in pattern. The rhythms of Earth grew less catastrophic, more predictable. It was in this balance that the anticipation truly began. Billions of molecules stirred in waters across the planet, bumped into one another, formed and broke links ceaselessly. Each second, countless experiments unfolded. Most vanished, unremarkable, returning to the chaos. But some held. A few arrangements proved stable, persistent, resistant to disintegration. Like the first faint sparks of a fire in damp wood, they glowed unseen, waiting for their moment to catch. If you had been there, wandering across endless volcanic plains or dipping a hand into warm, mineral-rich pools, you might have seen nothing remarkable. No greenery, no birds above, no creatures in the sand. Yet beneath the water's surface, history was being written in invisible ink. Every bond formed by chance, every replicating strand that endured against the odds, was a letter in the opening lines of life's story. The planet, once chaos, had become patient. It was content to rehearse, to wait, to refine, until the miracle was inevitable. To understand how life began on our planet, we must look more deeply at the basic ingredients, the building blocks of biology that emerged long before the first cells ever appeared. For billions of years before us, Earth was not a world of animals, plants, or even microbes. It was a world of chemistry, an immense theater of molecules colliding, breaking apart, and reassembling into new forms. Within this ceaseless dance, some patterns endured longer than others, and slowly, structure arose where once there had been only chaos. In this part of our journey, we explore those ingredients. For here lies one of the most astonishing truths: life is built not from rare or mystical substances, but from the most common elements scattered across Earth and the universe. Carbon, hydrogen, oxygen, nitrogen, these four elements, which form the majority of every cell in your body, make up the same dust that fills galaxies, the same matter forged from stars long before Earth existed. You are watching not only chemistry at work, but stardust learning to organize itself into breathing beings. The elemental foundation, imagine drifting in space. Between the stars is a near vacuum, and yet even here dust collects, carbon from exploded stars, ice crystals, silicate grains. With time, clouds of this interstellar dust collapse under gravity to form new suns and new worlds. Our own sun and Earth were born from just such a cloud 4.5 billion years ago. In that dust, the essential elements of biology were already present, waiting only for the right conditions. Carbon flexible, resilient, infinite in the structures it can create, became the spine of life's architecture. No other element is quite like it. It can form long chains, rings, and branching molecules without end, stable enough to last yet flexible enough to react. With carbon came hydrogen, the simplest atom, abundant everywhere, eager to bond. Oxygen joined, bestowing reactivity and energy, while nitrogen gave rise to complexity in molecules like amino acids and nucleotides. Add sulfur and phosphorus, and slowly you have the palette from which every living organism is painted. These were the elements the young Earth assembled, scattered in oceans, sky, and rock, each one essential to what was to come. A planet of energy, yet elements alone cannot build life. They are passive matter until set in motion by energy. On the young Earth, energy poured from every direction. The sun blazed above, weaker than now but fierce in its ultraviolet radiation. Lightning split the heavy skies in endless bolts. Within the crust, volcanoes erupted tirelessly, spilling lava and gases into the atmosphere, while beneath the oceans, hydrothermal vents pumped out both chemical and thermal energy. Even radioactivity from certain minerals contributed to the pool of forces shaping chemistry. Each of these energy sources acted as a spark, a trigger that drove atoms to rearrange themselves into larger, more complex molecules. Every storm, every eruption, every flash of ultraviolet light carried within it the potential to push molecules across an invisible threshold. And though most of these experiments dissolved back into the sea, some endured, quietly multiplying the library of possibilities. Imagine the oceans as a planetary laboratory, warmed by fire, lit by storms, stirred endlessly by currents. Millions of reactions happened simultaneously in every drop of water. Molecules encountered each other, sometimes bouncing apart harmlessly, sometimes joining together to create something entirely new. This process did not happen once, it happened trillions upon trillions of times, across millions of years. The improbability of life's chemical beginnings becomes less astonishing once you realize how vast the stage was, how many attempts were constantly unfolding across the whole planet. The first organic molecules, at some point during this long epoch, the first truly organic molecules appeared. Organic, in the language of science, simply means carbon-based molecules typically associated with life. But on the lifeless young Earth, they originated amid natural forces. Amino acids, the very molecules that build proteins, formed spontaneously from mixtures of methane, ammonia, water, and hydrogen exposed to sparks of energy. In the 20th century, scientists Stanley Miller and Harold Urey recreated these conditions in their famous laboratory experiment. Sealing simple gases in a glass vessel with water, they introduced electric sparks to mimic lightning. After a week, the liquid had turned brown with newly formed organic compounds. Among them were amino acids, the same molecules found in living cells. This experiment proved an extraordinary truth: the ingredients of life could emerge naturally, without design, from the conditions present on Earth billions of years ago. But life requires more than amino acids. Nucleotides, the building blocks of RNA and DNA, also had to arise. Sugars and lipids needed to form as well, molecules capable of storing energy and creating barriers. Evidence suggests that many of these molecules originated not only on Earth, but also fell from the skies. Meteorites striking the young planet carried complex organic compounds formed in the cold of deep space, adding to the growing inventory. Thus, the Earth's molecular recipe was enriched both from within and without, as though the universe itself conspired to write the first lines of biology upon our planet. The role of water held all of this together. It was the great medium, the solvent that enabled reactions to occur. Without water, life as we know it could not exist. Its molecules, bent and polar, formed delicate structures that allowed other molecules to dissolve, collide, and connect. Water moderated the temperature, cooled the hot surface, and circulated minerals. It shaped the very environment in which molecules learned to associate. More than this, water created cycles. It evaporated into clouds, condensed into rain, froze into ice, ensuring constant change. These cycles mirrored the rhythms that life itself would one day adopt, breathing in and out, consuming and releasing, growing and decaying. In this way, water was not only a backdrop but a teacher, rehearsing the patterns that biology would someday perform. The early symphony of chemistry, picture now the young Earth as an orchestra. Each section contributes its sound, volcanoes releasing gases, lightning striking oceans, hydrothermal vents spewing minerals, meteors delivering new elements from deep space. The planet's surface was alive with energy, and in its oceans, molecules ran through endless experiments. From this symphony came the first notes of organized complexity. Chains of amino acids, fragile but persistent, linked in warm pools. Fatty acids aligned themselves into spherical bubbles, creating rudimentary membranes. Thin strands resembling RNA began to assemble, capable of storing information in their structures. These were not yet life, not yet cells, but they foreshadowed what was approaching. They were like sketches before a final portrait, outlines of forms nature was patiently learning to perfect. The scale of time is staggering. For hundreds of millions of years, these processes unfolded, slowly, ceaselessly, always testing, always creating, always destroying. When one fragile arrangement failed, another took its place. Repetition allowed survival to improve. Variation allowed novel forms to emerge. This blind resilience, this endless cycle of trial, was the forge in which the ingredients of life became more than random chemistry. Nature's persistence, it can feel impossible to imagine such spans of time. Human lives are but moments compared to the epochs of early Earth. And yet, the persistence of nature ensured that what seemed unlikely eventually became inevitable. With trillions upon trillions of molecular collisions, it was only a matter of time before arrangements appeared that could endure long enough to change, to replicate, to build upon themselves. Once such arrangements arose, the story of life had already begun, even if invisibly. Look into your own body now, and you see these ancient ingredients still at work. The carbon in your cells links in chains hundreds of atoms long. Water fills your flesh, carrying nutrients and dissolving waste. Oxygen burns in your blood to release energy. Nitrogen holds the bonds of your DNA. These elements, gathered in chaos for billion years ago, now shape your every heartbeat. You are the living fulfillment of the ingredients' long patience. Transition toward cells. As organic molecules accumulated, something remarkable happened. They began separating themselves from their chaotic environment. Lipids spontaneously assembled into bubbles, forming membranes that encased water and molecules inside. These primitive compartments protocells shut substances in, shielding them from the outside. Within their fragile walls, reactions could happen more efficiently. It was a crucial step, for life requires not just molecules but boundaries, environments where growth can continue without constant interruption. Once compartments formed, other molecules slipped inside. Chains of RNA or bits of amino acids found themselves contained, and within that containment, a new layer of order appeared. Now reactions could be concentrated. Now molecules had space to work upon each other again and again, rather than drifting endlessly apart. It was here in tiny droplets invisible to the eye that chemistry inched closer to biology. The threshold of life, by the close of this age, Earth had become a planet overflowing not with organisms, but with potential. The seas brimmed with organic molecules of every sort, assembled through storms, vents, and meteorites. Protocells floated in warm puddles. Strands of primitive RNA flickered into existence, copying themselves imperfectly yet persistently. Though true life still awaited its first undeniable appearance, all the ingredients had gathered. The planet had written its recipe: abundant carbon, flowing water, ceaseless energy, enclosed membranes, replicating chains of information. The symphony was nearly finished with its overture, and soon the curtain would lift on the grandest act, the appearance of the first living cells. And so, in the silence of ancient waters, Earth prepared. It had drawn together everything required: its elements, its energy, its oceans, its patience. For billions of years it had waited, and when the time came, chemistry would cross the invisible line into biology. In that moment, unseen, unnoticed, irreversible, the Earth would change forever. The once lifeless stone planet would become a cradle, singing not only with storms and fire, but with breath. The Earth's patient rehearsal of molecules, stretching across hundreds of millions of years, had reached a moment unlike any before. For eons the oceans had been a restless cauldron, filled with amino acids, fatty compounds, nucleotides, sugars, and minerals, endlessly merging and dissolving as storms raged overhead and fire rumbled below. These were no longer random elements. They were ingredients woven together by cycles of energy, pressed toward patterns by the tides of chance and time. They had become something more than inert matter, though not yet alive. But now, imperceptibly, the borders between chemistry and biology began to blur, until finally they dissolved altogether. The first whispers of life emerged on the young Earth, and with them, the story of evolution would begin. It started quietly. In warm pools along volcanic coasts, lipids fell into arrangements that resembled fragile bubbles, each enclosing a droplet of the prehistoric soup. Their thin membranes offered something nature had not yet known: the ability to hold reactions together, to keep molecules concentrated in a space where they might interact more often. Many of these tiny spheres collapsed as quickly as they formed, but countless numbers drifted in the waters, and some remained intact long enough for something extraordinary to happen. Within a few of these bubbles, chance collisions gathered nucleotides into short strands that could carry simple information. In their primitive spirals, imperfect copies appeared, sometimes breaking apart, other times replicating again. They were not alive in the way we understand today, but they held memory, the capacity to record and transmit a pattern. It was here, within these fragile compartments, that the closest ancestor of all living systems shimmered into being. In one sense, there was nothing miraculous in the mechanics. Molecules naturally fit together where shapes and charges allowed. They bonded and unbonded following the silent logic of chemistry. Yet in another sense, everything miraculous was hidden in this moment, because one arrangement, among trillions of others, could endure and repeat itself not once but many times. a system that could persist against entropy, sustain itself through cycles of change, and leave echoes of its structure behind the foundation of what we call life. The difference between lifeless matter and living matter proved to be not a matter of substance but of organization, of persistence, of the ability to preserve a pattern in the face of destruction. As the ages passed, these protocells began to diversify. They were still fragile, still easily dissolved by heat and shock waves, but some sustained long enough to gather chains of amino acids along their membranes, forming primitive catalysts that quickened internal reactions. With faster chemistry, these protocells became factories of possibilities. They concentrated nutrients from their surroundings, processed them within, and sometimes split apart, releasing copies of themselves into the sea. Not every attempt succeeded indeed, almost none did. But the few that replicated reliably enough to leave descendants carved the first faint line that would later widen into the vast tree of life. The seas of the early Earth overflowed with these experiments. Countless bubbles swirled in the waves, each enclosing its own miniature cosmos of molecules. Each carried the chance of stability, the possibility of copying, the beginning of heritage. Some grew more resilient by incorporating stronger fatty membranes, others by making use of mineral surfaces, allowing internal chemicals to align into more organized networks. Still others relied on RNA-like strings that both stored instructions and catalyzed their own replication. The ocean had become a nursery of invisible pioneers, each carrying within itself the seeds of continuity. Slowly, through unrelenting time, error turned into advantage, and advantage accumulated into the first forms of evolution. It is astonishing to imagine such a world. No plants yet bloomed, no creatures stirred, no songs of life rose above the oceans. And yet beneath the waves, a drama unfolded unseen, a drama that would decide everything about the future of the planet. You might have looked across those waters and thought them barren, nothing but waves and storms. But had you possessed the eye of imagination, you would have seen universes within droplets tiny, fragile, and yet already bearing the promise of breath, of awareness, of thought. Every organism that would one day walk or swim or fly was folded invisibly within those ancient chemical spheres, waiting for the chance to unfold across time. The threshold of life was not crossed in a single moment, but gradually, in countless small steps. Each protocell that copied itself added another layer of refinement. Each mutation born of error enriched the diversity of forms that could exist. Some structures grew too brittle and perished quickly. Others adapted, finding resilience in simplicity. Over generations unimaginable in number, patterns stabilized. Protocells reached a point when their internal reactions no longer needed constant chance collisions. They had become systems with predictable rhythms, rudimentary metabolisms that converted energy into stability. It is difficult to identify the exact moment when lifeless chemistry became something we could call alive. And perhaps such a moment does not truly exist. Perhaps life was not an event but a continuum, a slow rising tide that eventually swept fully across the earth. Somewhere along this tide, the first true cell took shape. A bubble with a durable membrane enclosed strands of information-carrying molecules alongside proteins that performed basic tasks. Together they created not just a container but a self-sustaining unit, capable of consuming compounds from the environment and using them to replicate its own form. This was not complex life, not even multicellular life, but it was, undeniably, life. It could persist, respond, and reproduce not by the hand of chance alone, but through internal organization. From this moment onward, the Earth was no longer lifeless stone and ocean, but a world with inhabitants. Invisible inhabitants, microscopic and fragile, yet destined to rule the planet. These early cells multiplied across shallow seas and dark ocean floors. They carved out niches amid mineral deposits and hydrothermal plumes. In their struggle to survive, they learned cooperation as well as competition. Some absorbed sunlight more efficiently, beginning the slow path toward harnessing its energy directly. Others thrived in the shadows with chemistry drawn from rock and heat. Evolution was now alive, and with it, the never-ending process of refinement began. Every cycle of replication introduced small mistakes, and some of these mistakes gave their carriers an advantage in endurance. Those that endured left more descendants, and the cycle amplified. The tree of life grew its first faint roots. It is humbling to realize that all living beings, humans, trees, whales, insects, share ancestry with these early cells. Their simplicity belies their importance. Within their fragile structures, life had invented something astonishing: heredity. They held within themselves the recipe for making another like them, and they passed this recipe on endlessly across generations. Even today, in every cell of your body, echoes of those first recipes still whisper, imprinted in DNA, the descendant of the RNA that once carried memory through ancient seas. You are, in the most literal truth, a continuation of those first cells, their success extended across eons into thought and consciousness. Earth changed profoundly as soon as life appeared. The chemistry of the sea shifted, for living cells consumed and released compounds in new cycles. The surface began to record the marks of biology, microscopic fossils preserved in stone. Over millions of years, oxygen would slowly accumulate in the atmosphere, transforming the planet's skies. But in the earliest chapter, long before oxygenation, life was simple, anaerobic, content in the absence of breathable air. Yet simple did not mean unimportant. Here lay the foundation upon which everything else would stand. Picture again the vast silence of ancient Earth. To our eyes that world would seem empty, barren of the greenery and animals we associate with vitality. But beneath the still waters, entire populations of single-celled pioneers drifted unseen. They were small beyond perception, yet their effect was infinite. Each one represented an unbroken chain that stretched forward into forests and oceans alive with diversity, into continents filled with creatures, and eventually into the rise of humanity itself. Without their persistence, there would be no consciousness to wonder, no voice to tell this story. The transformation from chemistry to cells was the most important transition in the history of the Earth, though it unfolded without ceremony or audience. There was no light in the sky to mark it, no sudden change visible above the waves. It happened in silence, in the minutiae of molecules hidden within bubbles of fat. And yet from that silence, every sound of life has followed. It teaches us that greatness need not arrive in thunder or spectacle. Sometimes the most profound events occur quietly, invisibly, steadily, written only in the persistence of survival. As the ages rolled forward, life spread from pool to ocean, from vents to currents, making the planet gradually less alien to what we know. It was a fragile age, where extinction was always near, but the mechanisms of heredity and variation ensured that some line would push onward no matter the obstacles. Time itself was the greatest ally of these first organisms. With time, mistakes accumulated, with mistakes, novelty was born, with novelty, resilience grew. By slow steps, this dance of replication and mutation shaped forms better fitted to endure. Natural selection had begun its eternal work, and through its silent law, life became not only present but persistent. And so, the world changed forever, though no human eyes would witness it for billions of years. The border had been crossed. A lifeless planet had become a living one. From chemistry arose biology, from molecules arose cells, from the oceans arose inheritance. And within those first cells lay the entire potential of the future, the forests, the animals, the creativity of thought, the reaching of hands toward the stars. The earth had become more than stone and sea, it had become a cradle, and in its cradle a fragile flame flickered, one that would never again go out. The oceans of the earth, once silent cauldrons of fertile chemistry, had now been seeded with true life. Not complex creatures as we know them today, but single cells adrift in endless seas, their fragile membranes enclosing the most vital of secrets, the ability to preserve, to replicate, and to adapt. From the moment the first living cell endured, a new force had entered the universe, a force that would shape the destiny of this planet and, in time, produce consciousness capable of asking how it all began. But in these earliest days, life was still fragile, still invisible to the naked eye, and yet vast beyond our comprehension. For in every drop of ocean water floated billions of pioneers, each a vessel carrying forward the ancient experiment of survival. These organisms were simple, far simpler than any living thing you know. Their needs were modest, their forms unadorned. They required only a surrounding of molecules to feed upon and an environment stable enough to permit their divided existence. Yet their very simplicity was their strength. They could endure in realms of searing heat near hydrothermal vents, or in pools dense with minerals, or in the darkness beneath miles of ocean. They were hardy not in spite of their primitive forms but because of them. Nature had stumbled upon a solution both elegant and resilient: replicate, vary, endure. With that trinity, life had secured its place without ever needing perfection. The planet bore witness to an extraordinary transformation. Only moments before, on the cosmic scale, Earth had been a lifeless rock spinning beneath a young sun, its surface scarred with fire and stone. Now, life wrapped itself around the globe invisibly, blanketing oceans with populations of cells. The entire chemistry of the planet was beginning to change. When cells consumed minerals or gases, they transformed them into new forms. When they reproduced, they left not only descendants but also projections of waste into their surroundings. The oceans themselves began to taste different. The rocks near their shores bore microscopic stains of organic matter. Slowly, the planet was becoming not just alive, but shaped by life. Within these cells, the whispers of evolution grew louder. As copies formed over and over again, tiny errors accumulated. These errors were not flaws to be erased but opportunities to be tested. Some errors destroyed their carriers, dissolving back into the sea, but others made the cell hardier, faster, or more capable of grasping energy from its environment. Over millions of years, these differences expanded. Entire lineages formed, not by design but by survival. The first branches of life's tree spread through the oceans like invisible forests of possibility. For the first time in history, there was not one living system but many, entwined in ongoing experiments of endurance. The energy that powered these ancient cells came from diverse sources. Some organisms thrived on the chemistry of rocks and minerals, extracting electrons from iron or sulfur. Others hovered near volcanic vents, drawing power from hydrogen and methane. These archaic life forms were not photosynthetic as plants are today. They did not yet drink light from the sun. Instead, they thrived in the Earth's own furnace, using its deep heat and rich geology as fuel. In this way, they claimed territories across the seabed, marking their presence in layers of stone we can still trace billions of years later. Yet even as archaic life expanded across the oceans, new possibilities stirred. Accidents in heredity produce cells with membranes slightly stronger, with metabolism slightly more versatile, with more efficient molecules to copy and store information. The most notable of these changes was the invention of proteins, complex chains of amino acids that folded into shapes capable of performing subtle and precise tasks. Where RNA had once served both as information and as catalyst, proteins began to take over specialized roles, acting as enzymes that accelerated chemical reactions with astonishing efficiency. This innovation allowed life to process energy more rapidly, to build structures more robustly, to expand into realms once inaccessible. The complexity of the inner world of cells began to grow, preparing the way for the grandeur of biology yet to come. It is important to imagine this not as a single event but as an unfathomable stretch of time. For nearly 1 billion years, Earth was a world of microscopic creatures. No forests stretched toward sunlight. No fish patrolled the seas. The continents were barren, lifeless stone. Yet beneath the waves, and within every shallow pool, vibrant universes teemed invisibly, each cell a microcosm of reactions, each population a community adjusting to currents and climates. The world was in fact full of motion, full of replication, full of exchange. To the eye it seemed empty, to reality it was alive with incomprehensible abundance. Eventually, among the multitude of lineages, some cells stumbled upon one of the most transformative powers in the history of Earth. They learned to trap light. Pigments developed that could absorb energy from the sun, driving reactions within the cell to create fuel from carbon dioxide and water. This innovation, primitive photosynthesis, altered everything. For the first time, organisms were no longer bound to chemical reactions alone. They could drink the light of day, transforming it into stored energy, expanding into regions far from volcanic plumes or mineral springs. The very oceans glittered differently as these sun harvesters multiplied, capturing solar power and releasing their byproduct into the water. That byproduct was oxygen, a gas nearly absent in Earth's early atmosphere. At first it dissolved into the seas, reacting with iron to leave rust-colored stains in ancient rocks. Slowly, as photosynthetic life multiplied, the seas could hold no more. Oxygen seeped into the air. It was toxic to many of the older forms of life, which had no defenses against this reactive, destabilizing gas, and countless lineages perished. But others adapted, or found refuge in the shadows of vents where oxygen did not penetrate. And still others learned to breathe it, to use its power as fuel in cycles of astonishing efficiency. From this chemical revolution came a new path. The Earth's sky, once heavy with methane and carbon dioxide, began to glow with oxygen, and the stage was set for complexities beyond imagination. The rise of oxygen transformed not just biology but geology and climate. Layers of stone became rusted records of seas suffused with oxygen. The air itself shifted in composition, altering weather and the chemistry of rain. Life had turned the planet into something new, a biosphere, where living and non-living matter merged into one colossal engine. Earth was no longer lifeless rock hosting fragile passengers. It had become an organism in itself, pulsing with exchanges of energy and material between geology, water, air, and biology. And within this great organism, the earliest cells multiplied, diversified, competed, and combined. Communities formed, where different microbes drew energy from each other's waste, cycling molecules more efficiently than any could alone. In their cooperation lay the first ecosystems, invisible and simple, yet profound in implication. For from such consortia would eventually arise symbioses, the joining of different lineages into a single unit, each benefiting from the other's strengths. Out of this would come another miracle, the rise of complex cells, with internal compartments, with nuclei and mitochondria, with abilities far surpassing anything achieved before. But that belongs to a later chapter. For now, in the long arc of Earth's story, Part 5 stands as the age when life first truly ruled the seas, when the fragile flame sparked in protocells matured into robust populations that claimed the world as their own. The oxygen they released became the sky we breathe, the interactions they pioneered became the ecosystems that still frame our existence. Though unseen, though microscopic, these early organisms transformed the trajectory of an entire planet. Their echoes remain in every breath you take, in every heartbeat driven by oxygen, in every cell carrying the memory of their first resilience. The rise of early life was quiet, measured only in the passing of eons. But it was absolute. Earth, once barren, had been claimed. Life, once tentative, had secured its ground. From this foundation, complexity would grow like branches from a hidden root, spreading slowly into the vast flourishing that even now continues under our feet and above our heads. And so, the story marched forward not in haste, but with patience, with persistence, with a rhythm as steady as the surf of ancient seas. The seas had been the silent cradle of life for over 1 billion years. Cells multiplied in their darkness, drawing sustenance from minerals, from volcanic gases, from the hidden energies of the earth. For so long, existence had remained microscopic, the complexity of evolution hidden from the naked eye. But slowly, across unimaginable spans of time, something occurred that would alter both life and planet forever. A few organisms discovered how to trap sunlight more profoundly than before. They captured its photons not merely to gather warmth but to transform the very chemistry of existence. Harnessing pigments, these cells performed photosynthesis at a greater capacity, exhaling oxygen into their surroundings. This was not the first flicker of photosynthetic life, but now, its influence grew unstoppable. At first, oxygen simply dissolved into the oceans and reacted with iron, forming bands of rust that are still visible today in ancient rock. For millions of years, the seas consumed this strange product greedily, locking it away in layered stone. But as the photosynthetic microbes spread and multiplied, the oceans could hold no more. Oxygen began to leak upward into the air, changing the atmosphere molecule by molecule. And with its rise, the world entered one of the greatest revolutions in planetary history. Oxygen was, then, both gift and poison. For the ancient forms of life that had thrived in its absence, this new molecule was deadly. They had evolved in a world without oxidative stress, and the sudden flood of oxygen damaged their delicate systems, destroying lineages that had endured for eons. Entire families of organisms vanished into extinction, pushed into the corners of vents and shadows where oxygen could not reach. But to others, oxygen revealed itself as a treasure. Those cells capable of using it discovered a wellspring of energy, a means of burning fuel within themselves at far higher efficiency than before. With oxygen, life gained power, resilience, and the ability to grow larger than ever imagined. The peril of one age became the promise of another. This event, known through the silent testimony of rocks and fossils, reshaped the Earth itself. Skies that were once heavy with methane cleared, clouds shifted in formation, weather patterns evolved. Storms, rains, and climates changed as the atmosphere filled with this gas that would one day fill human lungs. The surface cooled, for methane, a greenhouse gas, was replaced by oxygen, altering the balance of warmth that wrapped the planet. Ice spread across continents, locking regions beneath long ages of cold, as though the Earth itself trembled under the scale of its transformation. But within this change lay opportunity. For the first time, life began to envision complexity. With the energy oxygen supplied, cells could power internal structures far beyond the reach of their ancestors. They grew larger, more intricate, inventing compartments within themselves, specializing functions. Some began engulfing others, not merely as prey but as partners, forming symbioses that endured. A great merging occurred, as once separate organisms fused into single new beings. One cell swallowed another without digesting it, and together they prospered. One became the host, the other the mitochondrion, the powerhouse that turned oxygen into an unending flow of usable energy. This union would echo through time, for it gave rise to the first eukaryotes, the ancestors of all animals and plants. The world of simple cells, dominant for 2 billion years, was giving birth to a new order. These eukaryotic cells were sprawling, labyrinthine structures compared to their simpler cousins. They harbored nuclei where information was stored, organelles where tasks were performed with precision, and cytoplasms bustling with motion. Their capabilities far exceeded what had come before. They could grow, divide, and specialize in unprecedented ways. The genetic creativity locked within their DNA blossomed, writing more complex scripts for survival. The Earth trembled subtly, for though there were still no forests or creatures, the potential for both had appeared in hidden oceans. Time continued its endless passage. Eukaryotic cells spread, multiplied, failed, and succeeded. They gave rise to single-celled organisms more adaptable and versatile than any before. But more importantly, they set the stage for a leap unimaginable in the older world, multicellularity. For once cells could cooperate within themselves, the idea of cooperating with others was inevitable. Colonies of cells experimented with shared existence, some dissolving easily, others tightening their bonds. Slowly, through trial and error across eons, a union formed that could endure generation after generation. Groups of cells specialized in tasks: movement, digestion, defense, each surrendering independence for the larger good. From those fragile beginnings, the first multicellular organisms appeared, simple in form but grand in implication. The oxygen revolution had shaken the Earth, sweeping away ancient dominions and clearing the way for new. It created room for vast possibilities in metabolism, shape, and size. And though it caused extinctions beyond counting, it also delivered the very breath that would one day fill lungs, the sky humans would one day gaze upon in wonder. With oxygen, the Earth drew closer to the world we know, a planet of blue seas beneath bright skies, awaiting its future passengers. Life stood now upon the threshold of visible grandeur, and the quiet symphony of evolution swelled into a crescendo of complexity. The ocean stood transformed. Invisible kingdoms of simple cells, both prokaryotic and eukaryotic, ruled every corner of their depths. And yet, an even greater experiment was unfolding, one born of cooperation and endurance. For billions of years, individuality had been the law, each cell surviving, replicating, and persisting on its own. But through shared bonds, a miracle stirred. Multiple cells began to form collectives, loose associations at first, fragile networks joined by the thinnest of threads. Within these groups they discovered strength that no individual could achieve alone. Some assemblies fell apart quickly, undone by conflict or instability. But others held together, accumulating advantages over time. Gradually, cells learned to communicate, to signal through chemicals, to recognize self from other. Cohesion allowed distribution of labor. Some cells absorbed nutrients, others focused on structural support, others defended the colony against threats. Through these divisions, whole groups endured where individuals might have failed. The principle of multicellularity had emerged, and with it, the dawn of body. At first, these bodies were modest, microscopic clusters adrift in the sea. They left little mark upon stone or fossil, dissolving too easily into time. Yet the principle was indestructible. Once begun, it repeated in lineage after lineage. Some colonial organisms grew into filaments, long strands stretching toward light. Others grew spheres, hollow within, capturing resources efficiently. In some, differentiation deepened further, reproductive cells devoted to heredity, somatic cells devoted to survival. The first division of function appeared the first whisper of tissues, organs, and forms. Over millions of years, shapes proliferated. Soft-bodied multicellular organisms spread thin across ocean floors, grazing upon microbial mats, filtering water for sustenance, leaving faint traces in ancient sediments. The Earth, for the first time, hosted beings whose bodies were visible, if only barely, to the naked eye. Their presence altered ecosystems profoundly. They created surfaces upon which other creatures could grow, shadows where others could hide. The principles of predator and prey, though not yet true in their later sense, had appeared in a nascent form of interaction. The genetic toolbox of these organisms expanded. Complex networks of regulation allowed multiple cells to arise from one fertilized beginning, arranging themselves into planned architectures rather than random clusters. Embryos emerged, tiny blueprints of form unfolding according to inherent instruction. The Earth was beginning to experiment with shape, symmetry, segmentation, branching. The laws of morphology, those patterns repeated across fish, trees, insects, and humans, were being drafted in invisible script within those early communities. None of this was rapid, none dramatic. Entire ages passed beneath seas where the most complex beings were still soft clusters only a few millimeters wide. But patience always favored life, and with deep time, even modest steps accumulated into revolution. Slowly, diversity reached a threshold, and the stage was set for events that would soon redefine the biosphere entirely. In the shadows of Precambrian oceans, the ancients rehearsed movements that would someday burst into the light as the Cambrian explosion. They laid the groundwork for the drama of animals and plants, for locomotion and predation, for skeletons and shells. The Earth, once silent of visible life, was preparing to bloom. And though no witness with eyes yet walked the shore, the oceans glittered secretly with possibility. Every drifting cluster of cells, every colonial experiment, every wrinkle of structure was a note in the symphony building toward grander music. For out of these associations would arise worms wriggling across sand, jellyfish pulsing through water, trilobites roaming the seafloor. Out of them would come forests and flowers, senses and minds. But in that early time, Part 7 remained a world of humble beginnings, where life had only just learned to join itself into bodies, and the vast spectacle ahead slept still within liquid dreams. For billions of years, the Earth's oceans had remained worlds of quiet experimentation. Life, though persistent and abundant in microscopic form, had kept almost all of its secrets hidden within cells too small for any eye to see. For endless ages, evolution unfolded in secrecy, confined to the invisible realm of bacteria and archaea, and the slow emergence of eukaryotic cells that quietly multiplied across oceans. The planet breathed, storms raged, continents shifted, climates warmed and froze, yet the surface seemed still barren of visible life. The seas, though filled with invisible voices of chemistry and respiration, appeared silent to any observer who might have been watching. It was a world where time moved in vast scales, where change was measured not by days or centuries but by stretches so long that continents themselves cracked, collided, and vanished before new forms of life emerged to take advantage of their shifting shapes. Yet in that silence, hidden beneath the waves, preparation was already underway for an event that would transform the Earth irreversibly. Nature had been rehearsing its symphony for billions of years, perfecting the instruments quietly, training the molecules and the cells through endless variation and selection. And then, in a sudden burst on the scale of geological history, the overture gave way to explosion. The Cambrian period arrived roughly 540 million years ago, and with it, the world awoke to a dawn unlike anything in its past. The stage that had waited patiently for so long erupted into brilliance. Life did not simply continue as before, it exploded into a diversity of forms so radical and so numerous that the Earth itself was reshaped. The Cambrian dawn was not an instant, but it was swift compared to the vast stretches of time that had come before. Over just tens of millions of years, a heartbeat measured in the eons of Earth life experimented with complexity in ways never seen before. Creatures grew larger, stronger, stranger, adorned with limbs, shells, and eyes. The seas, once quiet, became crowded theaters of motion. Predator and prey appeared, entwining life in a drama of survival that drove adaptation into swiftness. For the first time, animals consumed animals. For the first time, the fear of being hunted became an evolutionary force. Once life had been microscopic and hidden. Now it was visible, armored, motile, complex. The Earth had entered a new chapter, and the Cambrian oceans rang with movement and experiment as though the very planet had decided to dream out loud. Imagine descending into those ancient waters. Light from the young sun filters down into the shallows, falling upon reefs of microbial mats that have dominated coastlines for billions of years. But now, new shapes move across those mats, scraping their surfaces, boring into sediments, nibbling at each layer. Where once there was only stillness, now there are trails and shadows, marks of lives crawling and digging across the seafloor. Some are minuscule worms, threading their way invisibly into the mud. Others are trilobites, armored creatures with segmented bodies and protruding eyes, scuttling across the ground in groups, leaving tracks etched into sand that solidified into fossils we find today. Above them, jellyfish-like creatures drift, their translucent bells pulsing as they capture tiny prey with dangling tentacles. Strange, unearthly predators swim with segmented limbs thrust forward to seize their victims. Animalicaris, a creature more than a meter long, a giant of its day, set apart in size and power from almost everything else alive. These seas were vibrant, filled with creatures alien to modern eyes but united by the principle of innovation. Evolution, once slow, now accelerated in a storm of genetic creativity. Skeletons and shells appeared, structures of mineralized defenses that hardened creatures against predators. These were not small changes, they were radical transformations. In creating exoskeletons, life invented the fossil record, for in their hardness these forms endured across time, allowing us to find them 500 million years later. With shells, bodies could grow larger, withstand more force, open themselves to new methods of locomotion and survival. Complexity begat complexity, and competition spurred invention. Predators grew swifter, mouths sharper, prey grew harder, senses keener. The invention of eyes marked another miracle of the Cambrian. Light, once only a general guide for simple organisms, now became central to survival. Trilobites grew compound eyes capable of perceiving images, of detecting motion, of identifying predators before attack. With vision, life entered a new stage of interaction. The oceans grew not only noisy with movement but bright with awareness. For the first time, creatures could truly watch one another, seek prey deliberately, avoid death with foresight. The arms race of the Cambrian was not merely physical, it was sensory, cognitive, a race toward perception. Ecosystems emerged with clarity. On the seafloor, burrowers turned sediments, recycling nutrients. Grazers scraped algae and microbial mats, reshaping the foundation of marine food webs. Filter feeders lifted particles from the currents, capturing sustenance drifted down from above. Predators patrolled reefs, attacking the unwary. Every niche that could be occupied began to fill. Where once the sea had been a balanced but quiet bowl of microbes, now it had become a web of interactions, a net of energy transferring from one organism to another. The principle of ecology was born, not in abstract but in the teeth and shells and movements of Cambrian seas. Some of the creatures of this age are familiar to us. Sponges existed, filtering waters gently, their lineage stretching unbroken even into the present. The ancestors of arthropods, creatures that today dominate Earth as insects, spiders, and crustaceans, scuttled in countless forms, growing armor, jointed legs, antennae. Early chordates swam with flexible rods in their backs, the faint beginnings of spines, setting the stage for fish and, eventually, humanity itself. Others were strange, never to repeat: the Opobinia with 5 stalked eyes and a proboscis that plucked prey from the ground, the Hallucigenia walking on spines with appendages that seem bizarre even in our imagination, the Wiwaxia with a body capped in scales and bristling with rows of spines. These creatures burned bright in the Cambrian seas, many leaving no descendants, yet their forms testify to the incredible experimentation of life at its moment of sudden freedom. Why did the Cambrian explosion happen as it did? The causes are woven from many strands. The oxygenation of the atmosphere provided fuel for higher metabolism. The appearance of predators created evolutionary pressure that favored innovation. Genetic tools such as the Hox genes, controlling body development, unlocked new body plans that could be reshaped into diverse possibilities. Environmental changes opened niches across continents, flooding shallow seas with habitats ripe for occupation. Whatever the precise reasons, the result was undeniable: the world blossomed as never before. The Cambrian dawn changed not only the oceans but the earth itself. For as creatures grew and multiplied, they engineered their environment. Worms mixing sediments transformed the chemistry of seafloors. Reefs constructed from skeletal remains rose to shape ocean currents and ecosystems. Exoskeletons rich in minerals entered the cycle of erosion and deposition, binding geology even more tightly to life. The Earth had become a different planet, a planet visibly alive, a world where biological processes altered landscapes as profoundly as volcanoes and rivers. To imagine standing on the shore of a Cambrian ocean is to witness a scene at once alien and familiar. The air is still empty of birdsong, for flight is far in the future, and the land remains barren of forests or grass. Bare rock stretches into the distance, and waves crash upon beaches free of shells or seaweed. Yet just beyond the surf, a world of motion unfurls. Crustacean-like animals march across the seabed, strange armored worms wriggle, translucent jellyfish rise and fall with the rhythm of pulsing bells. Predators with claws and eyes race in pursuit of prey, stirring silty clouds as the drama of survival plays out. Every tide pulls forward life, every current delivers spectacle. It is the theatre of Earth's first age of visible creatures, a performance repeating endlessly beneath the sun. The Cambrian explosion did not last forever. Many lineages died as quickly as they appeared, swept into extinction by the unpredictability of climate and competition. Yet its impact never faded. From the multitude of experiments, some persisted, carrying forward principles that would define all future life. From chordates, vertebrates would arise, fish, then amphibians, reptiles, mammals, finally humans. From arthropods would come insects, spiders, crustaceans, the dominant forms of land and sea to this day. From mollusks would come octopuses, clams, snails. The foundation for all complex life as we know it was laid amid that great blossoming 500 million years ago. And so the Cambrian dawn remains a singular moment in Earth's history, a time when possibility burst into visibility, when nature's imagination leapt forward in cascades of symmetry and structure. Its creatures, bizarre yet beautiful, remind us of the unpredictability of life, the creativity that sleeps within every genetic code. They remind us too that our own forms, our spines and senses, our movements and minds, carry roots stretching back into those ancient seas. When you look at the fossil of a trilobite, with its ridged armor and compound eyes, you gaze not at a relic of something forgotten, but at a cousin, a member of the family of life that shared the same early experiments of body and mind. The Cambrian dawn was not the end, but a beginning, a threshold crossed, a door left open through which the future poured. Life had discovered form, interaction, awareness. It had discovered the art of visible existence, the drama of ecosystem, the ceaseless dance of predator and prey. In this exuberant plunge into diversity, the Earth became luminous with possibility. The seas would never be silent again, and from that awakening flowed every forest, every creature, every consciousness to come. For hundreds of millions of years, all of Earth's living beings remained bound within the oceans. The seas were generous, cradling organisms in their buoyant embrace, protecting them from dryness and the harshness of direct sunlight, offering endless dissolved nutrients within their waves. Within the water, bodies needed no great structural strength to resist gravity, delicate tissues could flourish without collapsing. It was, in a sense, the perfect cradle for the fragile beginnings of life. But though the seas had nurtured existence through eons, they could not contain life forever. Along the edges of continents, where waves crashed against stone and tide soaked the barren rock, an unclaimed kingdom waited. Land vast, silent, exposed, call to life with both danger and promise. And in time, living things would answer, crossing the shoreline and rewriting the story of Earth forever. The earliest pioneers desiring landfall were humble. Long before animals marched, plants advanced. At first, there were only small films of microscopic algae clinging to moist surfaces, painting the bare rocks green when tides receded. These microscopic communities could dry when the sun rose hot, only to revive when rain fell again. Though tiny, they represented a revolution, the first footholds of life upon land. From these beginnings, more ambitious plant-like organisms advanced. Mosses and liverworts grew in mats along damp shores, absorbing dew directly through their tissues. They lacked roots or stems, they hugged the soil for support and moisture. Yet in this modest way, land began to change. Stone once barren became softened with organic matter. Minerals leached slowly as dead tissue broke down, forming the first primitive soils that would allow larger greenery to thrive. Over millions of years, plants mastered new strategies. Some developed vascular systems, tiny tubes capable of carrying water upward from roots into stems and leaves. With this, height became possible. No longer confined to thin carpets along the ground, plants began to lift themselves toward the sun, unfolding fronds to drink its light more efficiently. Fern-like forests rose, their canopies shading the land. Roots dug downward, splitting rock, destabilizing landscapes, breaking stone into fertile soil. The barren continents cloaked themselves in green, exhaling oxygen into the skies, drawing carbon dioxide into their tissues. The atmosphere itself shifted again, its breath shaped by xylem and phloem, by leaf and root. Earth, once grey and sterile on its continents, blossomed now with forests that swayed to winds, rivers flowing between their growth. The coming of plants paved the path for animals. Insects and arthropods had already prowled the shallows, armored bodies evolved for crawling as much as for swimming. Some, like early millipedes and scorpions, ventured farther and farther inland, their exoskeletons protecting them from desiccation. They breathed through tracheae, fine tubes that carried air from spiracles on their sides deep into tissues. The land tested them harshly, with dryness, with cold nights, with no water to bear their weight. Yet their hard shells allowed survival, and soon they scuttled across forests, feeding on leaves, on fungi, on one another. As plants grew taller, insects grew wings, taking to the skies above the forests in flight that filled the air with the first true sound of buzzing. The conquest of land was no longer tentative, it had deepened into a permanent occupation. But the greatest step belonged to vertebrates. In the sea swam fish with thick, muscular fins, limbs with bone inside them capable of supporting weight. In oxygen-poor waters, some evolved lungs in addition to gills, enabling them to gulp air from the surface when suffocated beneath. With these twin advantages, limbs and lungs, came the possibility of escape from the sea. These lobe-finned fish edged across tidal flats, their fins pushing against mud, their breath drawn from air. What began as mere survival strategy became opportunity. One step led to another. Over generations, those that lingered longer on shore found insects to feed upon, found plants for cover, found niches with little competition. Slowly, fins became legs, tails stiffened for balance, lungs grew more efficient. By 370 million years ago, amphibians had entered forests, their limbs sturdy enough to carry them across land, their lungs drawing oxygen into their blood. Amphibians were pioneers but remained bound to water. Their eggs had no protection against dryness and had to be laid in ponds or rivers. Their skins required moisture, and they stayed tethered to wetlands. Yet they spread widely, their long bodies and stretching legs allowing them to patrol the margins of rivers, hunting insects, dominating niches once empty. Life had mastered the shoreline. Forests rang now with croaks and movement, with the steps of creatures large enough and strong enough to bend stone beneath their weight. Another innovation retold destiny, the amniotic egg. Some descendants of amphibians evolved a way to protect their young within hard or leathery shells, enclosing not only the embryo but its own reservoir of liquid water. With this, reproduction no longer depended on rivers. Species could march into the heart of continents, carrying oceans within their eggs. Thus reptiles arose. Their scales shielded them from drying winds, their strong jaws allowed them to dominate ecosystems, their eggs freed them from ponds. Reptiles conquered deserts, highlands, plains. They built empires of form turtles, crocodiles, lizards, eventually great dinosaurs that shook the earth beneath their weight. For hundreds of millions of years reptiles ruled, their conquest of land absolute, their shadows cast across every horizon. While animals diversified, plants too advanced. Ferns gave way to seed-bearing species, gymnosperms rising in towering forests that shaded vast landscapes. Seeds were a triumph like the amniotic egg, protective shells carrying nourishment inside, capable of traveling on wind or water into new ground. Flowers would not arrive until later, but already plants had armed themselves with tools for dominance, forging alliances with insects that pollinated them, shaping entire cycles of co-evolution. Forests thickened, soil deepened, rivers meandered through green corridors. The continents as we recognize them today were formed then, shaped as much by biology as by tectonic force. The conquest of land was not linear, not smooth. Climate changed, extinction swept across continents. The Carboniferous period left behind forests so dense that their fallen trees laid in swamps for ages, compressed later into the coal that humans burn in modern times. Giant dragonflies soared with wingspans a meter wide, thriving in oxygen-rich air. But eventually climate shifted, seas receded, deserts spread, and entire lineages vanished. Still, the principle endured. Life had broken the boundary of shorelines and laid claim to continents. No reversal could erase that triumph. The story of land did not end with reptiles. Mammals, descended from reptilian stock, would later inherit forests and plains. Birds, themselves the lineage of dinosaurs transformed, would fill skies with song. Angiosperms flowering plants would cover continents in spectacular beauty. But all of this was rooted firmly in that first bold step when plants pushed fronds upward from wet stone and when fish-turned amphibians took their first staggering strides. With each hesitant advance, the conquest grew permanent, until no corner of land remained untouched by life. The ocean still thrived, but they no longer held a monopoly. Earth had become truly a biosphere, alive from ocean depth to mountain peak. Imagine walking across a Carboniferous forest. Tree ferns tower above, their fronds stretching toward a sky hazy with humidity. The ground squelches underfoot with moss and mud, thick with early soils turned black by centuries of organic matter. Insects glitter in shafts of light, strange enormous millipedes crawl beneath leaves, amphibians croak amid swamps, dragonflies the size of hawks glide overhead. The air carries more oxygen than today, making fire dangerous but granting animals sizes that seem impossible. You are surrounded not by silence but by symphony, the hum of wings, the rustle of scales over leaves, the breathing of amphibians lurking in water. This is no barren world. This is life triumphant, reaching upward, outward, claiming the planet in green and flesh. The conquest of land reshaped the Earth irreversibly. It sealed the future of life as a planetary force, no longer confined to oceans but altering weather, climate, even the cycles of gases and rocks. Plants drew carbon dioxide from the air, cooling global temperatures and enabling climates where ice sheets advanced. Soil formed thick layers, binding nutrients and water. Rivers meandered differently, their bed stabilized by roots. Mountains wore different colors, rich with lichens and moss. The sound of wind across continents no longer echoed over barren stone but sighed through leaves, carrying the sense of life. 500 million years earlier, no creature had stood on dry land, no plant had breathed air, no insect had taken wing. Now, the continents had become ecosystems of unimaginable diversity. Evolution had not simply conquered territory, it had expanded the very definition of the biosphere. And from this moment on, there would be no turning back. The Earth itself looked transformed from orbit, the continents green and alive, the atmosphere thick and breathable, the pulse of oxygen steady and strong. We walk today across their triumph. The grass is beneath our feet, the forests over our heads, the insects that buzz endlessly in summer air, all are heirs to that first crossing. Every bird that lifts into flight carries the gift of those dragonflies. Every mammal that breathes carries lungs refined from amphibious ancestors. Every seed that sprouts in soil carries the invention of ancient mosses and ferns. The conquest of land is not simply a story of the past, it is a continuity still unfolding, a triumph woven into the ground and air we share. From the earliest sparks of chemistry in the ancient seas to the towering forests and creatures roaming the continents, life on Earth has never once faltered in its continuity. Through billions of years, despite extinctions, despite upheavals of ice and fire, despite cosmic impacts and shifting continents, the unbroken chain has endured. Each organism carried within itself a story that reached back into the past, and in the act of reproducing, each organism preserved that story anew. Continuity is the greatest miracle, the reason we stand today able to recount this tale. Without it, without the patient persistence of cells passing their patterns forward, no tree would shade us, no bird would sing, and no thought would flow through the human mind. It is humbling to consider where that continuity began. In the earliest protocells, fragile bubbles adrift in shallow seas, molecules discovered how to preserve form against entropy. They developed ways to keep information stable long enough to replicate, long enough to endure another cycle and another after that. When oxygen swept the planet like a tidal wave of change, life endured by bending to its challenge. Some fled into anaerobic refuges, others perished, but many seized it as an opportunity, evolving mitochondria to harness its deeper power. When ice ages wrapped the Earth in frozen sheets, only the hardiest survived, clinging in volcanic refuges or shallow equatorial waters. When asteroids crashed and firestorms spread across continents, killing nearly everything large, bacteria remained hidden in soils, spores protected in cracks, seeds waiting in darkness for a time to bloom once again. Continuity is not the survival of individual beings, but of lineages. Every organism you have loved, every tree that has shaded your path, every creature that has passed under your gaze is the latest chapter of a story 4 billion years deep. Each is cosmic memory wearing flesh. This miracle is not delicate but unyielding, tested in the harshest furnaces time can offer. Continuity resists extinction through resilience of form, through flexibility of genes, through the indomitable geometry of survival itself. Extinctions, however violent, have never broken the chain. More than once, Earth nearly erased its living mantle. Over 250 million years ago, at the end of the Permian, 90% of species vanished as the world overheated, seas suffocated with hydrogen sulfide, and forests fell silent. Yet life held on, hidden in shadows of volcanic rock, buried in sediments, tiny microbes persisting until the storm had blown itself away. 66 million years ago, a meteorite struck what is today the Yucatan Peninsula, igniting wildfires across the planet, spreading dust that darkened skies, and extinguishing the great lineage of dinosaurs that had ruled for over 160 million years. And yet, tiny mammals already alive in their burrows emerged, nourished their young, and became the ancestors of future lineages, including ourselves. In every catastrophe, survivors wrote continuity anew, carrying memory forward across the abyss of loss. Continuity is not static repetition. Genes mutate, organisms adapt, and diversity explodes. But across change lies an unbroken thread of inheritance, weaving all beings into a single tapestry. Look into the genetic code of a bacterium, of a fern, of a whale, of a human, and you will find the same alphabet of life. Written in those letters is the testament of kinship. We are not strangers to the forests or oceans, we are their brothers and sisters, descended from the same first cells that struggled in silence. The miracle is not only that life continues, but that it continues as one, united in ancestry, diverging in form but knitted together by shared origin. When humanity emerged from the African savannas, carrying stone tools and fire, it did not break from this continuity but extended it. Our thoughts, our language, our ability to contemplate the stars are evolutionary achievements no less than wings in birds or photosynthesis in leaves. We invent, we explore, we reflect, and in doing so, we serve as the consciousness of all the life that came before. Within your own cells, each mitochondrion is the descendant of ancient symbiotic bacteria. Within your own genome lie fragments of viruses that fused with your ancestors and became part of the inheritance of life. You are an archive, a living museum of history written in biology, carrying forward echoes of every age the Earth has known. This awareness should stir humility. The continuity of life is far older than humanity, and it will endure far beyond us. Should our species one day falter, fall silent upon this blue planet, the line will not end. Bacteria will multiply, insects will crawl, trees will spread seeds into soils, and other creatures will write their own stories upon the canvas of time. Continuity is not merciful or cruel, it is simply unbroken, flowing forward with indifference and majesty alike. We are a moment within it, blessed to be conscious enough to marvel at it. But for now, continuity includes us. It includes every birth in every nest, every sprout breaking from soil, every cell dividing in the hidden depths of coral reefs. It includes the pulse within your wrist and the breath rising in your chest. All of this, your heartbeat, your breath, your thought, are living proof that the chain has not broken. You hold within you the flame kindled billions of years ago in a shallow tide pool beneath a storm-swept sky. That flame has never gone out. It burned in organisms blind and simple, in trilobites scuttling across Cambrian seafloors, in amphibians trembling at the shore, in reptiles sunning themselves upon rock, in mammoths roaming glacial plains. And now, in you, it burns still, asking where it began and grateful that it continues. Continuity has also shaped the very face of the earth. Mountains wear the dust of forests that grew and died upon their flanks. Coal seams record the bodies of trees that lived 300 million years ago. Limestone cliffs are the recollections of coral reefs built in vanished oceans. The shape of continents, the chemical balance of air and sea, the fertility of soils, these are geological footprints of life's persistence. Continuity is not just biology, it is the living geology of the planet, sculpting the home upon which it endures. As you close your eyes and imagine the unspooling of this story, feel yourself within its current. It is the same current that carried fragile protocells through storms, that bore trilobites across ocean floors, that helped amphibians to stumble awkwardly but persistently onto new continents. It is a current that carries humanity across challenges now, binding our struggle to survive with all survival that has come before. You are not separate from it. You are not an accident floating apart. You are its living continuation, the inheritance of success written and rewritten across 4 billion years. The miracle of continuity is not only that life endures, it is that it creates meaning. Think of the possibility that a universe of matter and energy gave rise to creatures capable of reflection, memory, and love. Continuity carried not only survival but awareness. It brought forth the ability to wonder at stars, to invent art and song, to whisper stories at night by the flicker of fire. Continuity does not know what it makes of itself, yet it produces minds that can open books of fossils, look back across time, and say, "We belong to this." And when night falls, when storms rage, when moments seem fragile, remember this: life has endured every catastrophe before, and it continues still. Continuity will fold every hardship into memory and keep moving onward. You carry within you a resilience as ancient as the earth, as persistent as oceans, as indelible as time itself. That continuity is not simply a fact, it is a gift, one that gives every moment its unbelievable significance. From stardust to cells, from oceans to forests, from silence to consciousness, life's line has never broken. This is the grandest miracle of all, that existence continues, that patterns endure, that we are here, breathing, thinking, listening to the story of origins. Continuity lifts you upward, ties you backward, and carries you forward into futures yet to be written. It is the flame that cannot be extinguished, the melody that never ends, the ultimate answer to the question of how life began. For life began not as a one-time event but as a river, and it has been flowing ever since, without pause, without break, without surrender. And you alive in this moment are part of its eternal stream.